Om Swastiastu, Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. On this occasion, we will discuss about Hamiltonian Circuit Problem, and before we start our presentation, let me introduce ourselves first. Starting with me, my name is Kadek Wahyu Ardia Putra with student ID 24151010002, and my partner.
My name is Indra Pandika with 3-digit student ID is 012.
And my name is Danvi Suwatno with student ID 24151101055.
Okay, now we jump into the material. Okay, for the first material will be presented with my friend. Times is yours.
Okay, thank you for the time. So here I will explain the representation of graph structure using adjacency matrices, which are used in this Hamiltonian Circuit program. Next. Okay, so in this program, the graph structure is digitally represented using an n times n two-dimensional matrix data structure, commonly known as an adjacency matrix. And the variable n here represented the total number of vertices directly input by the user when the program is first run. In a computer system, these vertices are not represented by letter, but rather by row and column indicates of the matrix, starting from vertex 0, 1, 2 up to vertex n-1. Meanwhile, the relationship between vertices, or what we call edge, are determined by binary value within the matrix coordinate. A1 indicates that there is a direct edge or path connecting the two vertices, while A0 indicates that there is no direct path between them. Next. Okay, to make it easier for understanding, let's look at example of 5x5 adjacency matrix on the screen. For example, let's look at row 0. There is A1 in column 1 and column 4. This means structurally node 0 is directly connected to node 1 and node 4. Meanwhile, column 2 and 3 have a value of 0, meaning node 0 does not have direct access to those nodes. This matrix structure serves as the primary foundation for the program's algorithm. Within the isValid function, the program will always check this coordinate condition. If the algorithm attempts to jump to a specific node but that node has a value of 0 in the matrix, the move will be immediately rejected because it is considered structurally impossible. Next. And now, after looking at the binary numbers in the matrix on the previous slide, the image in the screen is a visual representation of it. Each green circle number from 0 to 4 represent a node or vertex, while the line connecting them represented edge or connection between those nodes. If we compare this with the analysis of row 0 from earlier, you can clearly see that node 0 is directly connected by a thick blue line to node 1 and node 4. Meanwhile, its connection to node 2 and 3, which have a value of 0 in the matrix, are depicted here with gray dashed line, indicating that there are no active direct paths. This physical visualization serves as the initial map for our algorithm. And from this visual structure, we can also observe several unique characteristics of the graph we are using, as I will explain in the next slide. Next. Okay, so based on the program code we designed, the resulting graph has two main characteristics. The first characteristic is graph and undirected graph. This means the relationship between nodes are bidirectional or symmetric. In the program code, this characteristic is implemented using the ngraph function from the network X library, as shown in this code snippet. So if node A is connected to B, then node B is automatically connected to A. And the second characteristic is this graph is an unweighted graph. Since this graph structure only stores binary value of 0 and 1, the program only query whether a path exists or does not exist without calculating distance, because our specific load value on that edge of the graph. Okay, that's all explanation from me. For the next session, Danvi will be explain more detail. Thank you.
Okay, thank you, Indra, for explaining the graph structure. And in this section, I will break down how our program execute the graph to find the Hamiltonian circuit. So the algorithm we are using is backtracking. You can think of this algorithm like someone trying to find their way out of a maze. The program will keep moving forward from one node to another. And if it hits a dead end, or for example, there is no path to the next city, or the next city has already been visited, so it will take a step back, which we call a backtrack, and try a different turn. Next. So before the program steps to the next node, it must pass a validation check called the isValid function. There are two absolute conditions here. First, the program checks the adjacency matrix that Indra already explained before. If the value is 1, if it's 1, it means a path exists. Second, the program checks if the destination node is already in the temporary path. If it is, the program won't go there. This is to prevent repetitive loops before all nodes have been visited. Next, so this is the root search simulation. First, from node 0, the program sees available path to nodes 1, 3, and 4. The program will always try the smallest number first, so the path becomes 0 to 1. Like that. And from node 1, the available paths are to 0, 2, and 3. Since 0 has already been visited, the program chooses 2, and the path will become 0, 1, 2. From node 2, the program explores available path and selects 4. Then 4, it selects 3. So our temporary path will be 0, 1, 2, 4, and 3. Next. Just like this. So all 5 nodes has been successfully visited without stepping on the same node twice. And the final and most crucial step of this Hamiltonian circuit is, can we return to the starting point? So when the number of nodes in the path reaches 5, the program enters the base case. The program will check our last point, which is node 3. And does node 3 have a path back to node 0? If we look at the matrix in row 3, at the column 0, the value is 1. This means there is a way back. Since the condition is met, the program stops and prints the discovered circuit. 0, 1, 2, 4, 3, and back again to 0. That concludes the demonstration of the search process of our code. And then we'll go to do a program demonstration. Okay, so at first we have isValid function. It is to check if there is an edge to the vertex, and to check if the vertex is already visited. And then there's a time cycle function, or a function of the recursive backtracking. It is to check if there is a path that goes to the starting vertex. This is where the backtrack is proceed. And then this is the function that make the program dynamic, or based on user input. User can input how many they want a vertex that been processed, and then there is input of an adjacency matrix. So user can input how many vertex that they want and what is the adjacency matrix. And the output for this program is to print a solution of the Hamiltonian circuit problem and the graph visualization. Maybe now I will just run the program and show it to you. Based on the example of Hamiltonian Circuit Problem by Indra, it has 5 vertex and the agency matrix. So this is the visualization of the graph, and this is the print of the solution of the Hamiltonian Circuit Problem. Okay. So here, you might notice that our code outputs the circuit 0, 1, 2, 3, 4, and 0 again, which is slightly different from the example in the PowerPoint. Well, this is the perfect demonstration of how backtracking works. Since node 2 is connected to both nodes, both node 3 and node 4. Our algorithm explores them in numerical order. It successfully finds a complete circuit through node 3 first. Because the Hamiltonian circuit problem only asks to find any valid circuit, the program terminates and returns this first successful path. So basically, this agency matrix for this problem has 2 solutions. The first one is 0, 1, 2, 3, 4, 0, and the second is 0, 1, 2, 4, 3, and 0 again. And in this program, it prints out the first solution that are found, and the first solution that are found is 0, 1, 2, 3, 4, 0, and that's it. And for the next step or the next explanation will be explained by Wahyu.
Okay, Danvi, thank you for the explanation before. Now that we understand the basic structure of our graph, and let's dive into the core concept of this problem and the difference between a Hamiltonian path and a Hamiltonian circuit. Okay, first, a Hamiltonian path is a road in a graph that visits every single vertex exactly once. And it is important to note that a path does not necessarily have to return to where it started. As you can see in this picture, this is graph of the Hamiltonian path and start from 6, 1, 3, and 4. And for the other hand, a Hamiltonian circuit, which is the focus of our project, is essentially a Hamiltonian path with one extra requirement. There must be an edge that connected the very last vertex visited back to the starting vertex, forming a complete closed loop. As you can see in this picture, this is the Hamiltonian circuit, and starting with 0 and close with 0 again. Okay, the Hamiltonian circuit problem is well suited to be solved using the backtracking algorithm because this method searches for solution by building a path step by step while checking every possible choice. Okay, you might wonder, why did we choose backtracking to solve this? Okay, let's look at how the algorithm actually works. Okay, the backtracking method searches for solution by building a path step by step while checking every possible choice along the way. Specifically, the program selects vertices one by one to form a potential path. For every vertex we pick, the algorithm ensures 2 things. First, it must be connected to the previous vertex, and second, it must not have been visited before. Okay, if we hit a dead end or pick an invalid vertex, the algorithm is backtracks to the previous step and tries a different possibility until a solution is found. Okay, beyond just how it works, there are 3 main reasons why this approach is superior for this specific problem. Okay, first, it is highly effective for combinational searches. is a Hamiltonian circuit has many possible paths, so a systematic search method is needed. Second, it prunes invalid path early. Paths that do not satisfy the condition are stopped immediately without continuing unnecessary searches. Finally, it is more efficient than brute force. As backtracking avoid checking all possible permutation completely, making the search process faster and more efficient. And then let's take a look at how this logic is actually written in our Python implementation. And as you can see in our code, you can see the backtracking mechanism right here. We first assign a vertex to the path using path post equals v. And we then recursively call the function to move to the next position. If it returns true, we found our circuit. However, if that path fails, we perform the backtrack step by resetting that position to -1. This allows the algorithm to try the next availability vertex in the loop. And to wrap up to the technical analysis, let's summarize the condition that make a path valid in our program. And in our program, a path is considered valid if it satisfies this condition. The first condition is edge availability. There must be a direct connection from the current vertex to the next one. For the secondly is unvisited vertex. To maintain the Hamiltonian properly, the vertex must not have been visited before. For the third condition is circuit condition, and this is the final checks. And after visiting all vertices, the last vertex must connect back to the starting vertex to form a Hamiltonian circuit. And that concludes our explanation of the Hamiltonian circuit problem. Thank you for your attention. We hope this explanation provides a clear insight into how backtracking solves this complex graph problem effectively. And we close with Param Santi. Om Santi 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 Om. Wassalamualaikum warahmatullahi wabarakatuh.